Welcome to the Explainer. Today, we're going to break down a topic that, let's be honest, often trips people up in software engineering interviews: data modeling. If the whole idea of designing a data schema from scratch feels a bit intimidating, you're in the right place. We're about to give you a playbook to make it feel way more straightforward. You know the scenario, right? You're asked to design some massive system, and suddenly the data model feels like this huge, undefined block. Where do you even begin? Well, we're going to walk through a clear, step-by-step playbook inspired by a former Meta staff engineer that will give you the confidence to totally ace this part of the interview. So, what are we really talking about here? At its core, data modeling is just the process of deciding what your database tables will be, how you'll find records in them, and, this is the most important part, how those tables connect to each other. Think of it as the actual blueprint for your system's entire data layer.
Okay, let's dive into step one of the playbook. Before we even sketch out a single table or column, we have to make the most foundational decision of all. Where is this data going to live? This one choice is going to shape everything that comes after.
Now, what's so interesting here is the fundamental trade-off. While there are tons of database types out there, the choice in an interview pretty much boils down to these two. On one hand, you have the structured, rigid world of a relational database. On the other, the flexible, dynamic schema of a document database.
So here it is, the key takeaway for your interview. Resist that temptation to pick some exotic, fancy database just to seem impressive. A standard relational database like Postgres is almost always the right call. It's a safe, totally justifiable choice that lets you focus on the data model itself, not on defending some niche technology.
All right, so we've picked our database, trusty old Postgres. Now it's on to step two, building the actual blueprint. And this all starts with two concepts that are the absolute bedrock of any relational model.
First up, the primary key. It's a super simple but incredibly powerful concept. Every single row in your table gets its own unique ID. This is your guarantee that you can always pinpoint one specific piece of data with zero ambiguity.
And this is how we connect all the dots. A foreign key is the glue that holds your tables together. It's simply a field in one table that points to the primary key of another one. This creates the relationship and, crucially, prevents what we call orphaned data. Like a comment that belongs to a post that's been deleted. Okay, let's make this real with a simple Instagram example. Our first entity is the users table. See that ID column? That's our primary key. Every user gets one, and it's always unique. We've also made the email unique, which is a pretty common and really important practice.
Okay, now let's add posts into the mix. The posts table has its own ID as a primary key, of course, but look closely at that user ID column. That's our foreign key. It points right back to the ID in the users table, which creates this crystal clear link between a post and the person who created it.
And this is a brilliant illustration of how you handle more complex relationships. The likes table is a classic join table. It doesn't even need its own primary key. Instead, its whole job is to connect users and posts using two foreign keys, one for the user who liked it and one for the post that was liked. This setup is the standard way to model a many-to-many relationship.
Hey, here's a pro tip that's going to save you a lot of headache in an interview. Don't get bogged down trying to label every single relationship as one-to-many or many-to-many. Seriously, it's not necessary. If you just define your foreign keys correctly, the relationships become totally obvious. Focus on the implementation, not the academic buzzwords.
Okay, so that brings us right to step three. We've got our tables, we've got our relationships defined. The next big principle is all about keeping our data clean and consistent. And your default starting point here should always be a normalized model.
So what does normalized even mean? Well, to put it simply, it means you store each piece of information in exactly one place. That's it. For example, a user's name is only stored in the users table. The opposite, denormalization, is when you deliberately duplicate data, like storing the username on every single one of their posts, just to speed up reads. But that comes with a huge risk of data getting out of sync.
So here's your rule of thumb. Always start with a fully normalized model. Denormalization isn't a design choice you make from the get-go. It's a performance optimization strategy. You should only use it to solve a very specific bottleneck, and even then, it's often better to do it in a separate cache, not in your primary database.
And that leads us perfectly into step 4, performance. Before you even think about denormalization, there's a much better, much safer tool you should always reach for first: database indexes.
So how do you know what to index? Well, the best practice is to work backwards from your APIs. If you have an endpoint that needs to fetch all posts for a given user, just ask yourself, how does the database find that data? Without an index, it has to scan every single row in the posts table. But if you just add an index to that user ID column, you give the database a direct lookup. It's like a table of contents, and it makes that query incredibly fast.
Now, indexes are great for optimizing queries, but what happens when your data becomes so massive that it won't even fit on a single machine anymore? This is where step 5 comes in, sharding.
Okay, the golden rule of sharding is to pick a shard key that keeps related data on the same machine. For our Instagram example, let's say we often need to fetch a post and all of its comments together. Well, in that case, we'd want to shard both the posts table and the comments table by post ID. This makes sure they all live on the same server, which helps us avoid really slow and expensive cross-shard queries.
So, to wrap this all up, here it is, the complete 6-step playbook. It's a logical path from the highest level decision all the way down to specific optimizations. First, choose your database. Second, outline your columns. Third, define your keys. Fourth, add indexes based on your APIs. 5, only consider denormalization for specific performance reasons. And finally, 6, plan your sharding strategy if you're dealing with massive data volume.
By following this playbook, you're not just building a good model, you're showing a methodical, professional approach. You've built a solid foundation. And you know what the best part is? That frees up your mental energy to confidently tackle the next challenge the interviewer throws at you. So, with a solid data model in place, what's the very next bottleneck you would start thinking about solving?